Hi everybody. Today the first thing I want to tell you about is test 3, which is coming up on Tuesday, this Tuesday, April 28th. It will cover section 4.4 through section 5.3. Today we will cover 5.3, and this will be the end of chapter 5 for us. So the tests come pretty close together here at the end of the semester after having a 2-week break in the middle there. So get ready for that. The test will be conducted on MML, just like quiz 4 was conducted on MML yesterday. Now, today we want to look at solving exponential and log equations. First topic is solving exponential equations using logs. Now we've been solving them without logs, but in order to do that we always had to have the same base, if you think about it. Let's look at this example 1 here. We're asked to find t, and I say, oh, t is up in the exponent, so yeah, we know what to do. We'll divide each side by 150 first of all and get rid of these big numbers. And I get 20 equals 10 to the 4t. Okay, but at this point I realize I've got a different situation. The base here is 10, the base here is 20. There's nothing I can do to change that, so there's no way I can get exponents equal to each other like we've been doing in the previous exponential equations that we solved. But now that we have logs, we have the tools to solve this. Let's take the log of each side to that base there, 10. So in other words, a common logarithm. So the log of 20 equals the log of 10 to the 4t. Now we know from our properties of logarithms that the log of b to the base, the log of b to the x to the base b is just equal to the exponent, x. So it's property number 3. In other words, this is just the same as 4t, and that's what I wanted. Now the variable is no longer stuck up in an exponent, it's down in the main part of the expression. So, log of 20, that's a number that I can look up on my calculator. I can just key in common log of 20 and it will give me some decimal number. So, solving for t, I get t equals log of 20 over 4. If I key in log of 20 on my calculator and then divide that number by 4, I will get 0.3256, at least when I round to the 4th decimal place there. So that's why I have the squiggly equal signs to indicate I'm approximating. This number might in actuality go on much longer, even forever. Now, that's how you solve this type of problem algebraically. Let's look and see if you could use a graphing calculator to get the solution. In part B of this problem, we'll look at the graphical approach. If we called one side of the equation y1, then we could create, or y2, it looks like I called it, we could create a function. We could say y2 equals 150 times 10 to the power 4t. The graph on your calculator would look like that. All right, typical exponential curve where the base is greater than 1. Then if I think of the other side of the equation as a function, I could say, okay, y1 equals 3,000. That's a function. It's a constant function, so it's just a horizontal line. I can look on the calculator and see where the points intersect. If you're using the Desmos program, just click on either one of these two curves here, either the green one or the black one, and then you'll be able to trace along and see what the point of intersection is. And the point of intersection looks like this, 0.3253, 3,000. So that tells you that when t is equal to 0.3253, we get our result, which is a little different from what I have written here. This should be 32526. I lost a digit over here. So when you round this up, you would get that 3 that we're seeing in the 4th decimal place there. Now we actually have 5 decimal places here. Okay, so go ahead and work one of these out. Do problem number 10 on page 354. You want to solve it algebraically and then solve it graphically too. Look at the graph to see that the graph confirms what you have figured out algebraically. Okay, how did you make out? Problem 10 says this. 9,000 equals 400 times 10 to the power x. Well, the first thing I notice is that I have all these ugly zeros all over the place. If I divide each side by 100, I can at least simplify these numbers and get them smaller. So I divide by 100, so these two zeros cross out, these two zeros cross out, and I get 90 equals 4 times 10 to the x. If I divide each side by 4, then I get 22.5 equals 10 to the x. Again, the bases are different. I take the log of each side to the base 10 because 10 is my base here in the exponential expression. That gives me log of 22.5 equals x, right? I've gotten the exponent down here. Tap on my calculator and I get the approximation for that. X is approximately equal to 1.352. Good. Now part B says confirm this graphically. If I call this expression on the right 400 times 10 to the x, if I call that y1, then here's my function, this exponential curve here. Looks something like that. So then the expression on the other side of the equation, I'll call that y2. In other words, I'm saying let y2 equal 9,000. So it's that horizontal line going along like that at level 9,000 here on my y-axis. If you trace along the function and get the point of intersection, you'll see that it is in fact 1.352. That's where the x value is. Good. Let's look at change of base. It is possible to have a log with one base and convert it into a log with different base, which is a good thing because on calculators you're only going to see your common log key, where your base is 10 of course, and your natural log key, where the base is e. Well, we have this formula. The log of x to the base a is equal to the log of x to the base b divided by the log of a to the base b. That is on page 347 of your textbook. Now, you can really take advantage of that if you convert logs that are to various bases, convert them to either this or this, because once you do the conversion, then you can use your calculator keys to get your answer. So, if you start off with the log of x to some number a, you know that this is true. This equals the log base 10 of x divided by the log base 10 of A. If you don't want to tap on that key and you want to tap on that one instead, this is also true. Here, my base is E. So both of these expressions are also equal to the natural log of x divided by the natural log of A. How would you use this? Let's look at example 4. Evaluate, this is part A, evaluate the log of base to the base 8 of 124. Now, of course, we don't have a key in our calculator that will let us take a log to the base 8. So we convert. We convert, in this case, in this example, to the log base 10. So using this rule up here, I take something that's log base 8 and I can convert it to something that's log base 10 over log base 10. I get these two numbers from my calculator. There's the log of 124 base 10. There's the log of 8 base 10. And if I simplify this, just divide one into the other, the approximation becomes that, 2.318. Now notice that we could also have used natural log, right? Instead of converting it from here to here, I could have converted from here to here. In which case, what I started off with, log of 124 base 8, could be written as natural log of 124 over natural log of 8, which is approximately equal to 4.820 divided by 2.079. Do that computation on my calculator, and I get 2.318, which matches what I got there. Now, you work one out. Do problem number 12 on page 354. Number 12, page 354.